Let's take a look at this example here. We have a population in thousands of a certain species of wildcats at time t in years, and that is modeled by this function right here. This is a piecewise function because there's three separate pieces. Piece number 1 exists when t is between 0 and 5. That's our piece number 1, and the function is going to be 10. Piece number 2 is when t is between 5 and 8, and the function is this parabola, this quadratic. And piece number 3 is when t is greater or equal to 8, and that is this function right here. Part A, we want to sketch the graph of p of t. So I already have the axes down here. T is in years, so 1 year, 2 years, 3 years, and so on. P of t is the population in thousands. Now, for a piecewise function, we have to graph each of the pieces. The first piece happens between t equals 0 and t equals 5, which is give or take somewhere around there. So now we can sketch this in. Between t equals 0 and t equals 5, the function value, or the y value, if you want to call it that, is going to be 10. So it's a consistent, constant function of 10 like this. Now, for piecewise functions, we have to check our endpoints. So at t equals 0, do we know what the value is? Well, t equals 0 is included in this part. So at t equals 0, we have the function 10, or the value 10. So that's a solid dot. But at t equals 5, it actually switches over to the second piece. It's right here. So that means that I'm going to have a circle right here, because I don't know what's happening at t equals 5 just yet. Now let's move on to the second piece. That is when t is between 5 and 8. And we have this quadratic function that looks like this. This is a parabola that opens up, so it's a right side up u, and it has a y-intercept of -40. Now, it doesn't make sense for us to graph all the way down to the negatives because we can't have a negative population. Instead, I have a trick for you. And this trick is to sub in the endpoints t equals 5 and t equals 8. So I'm going to quickly do that on the side here. So p at 5, let's see what happens here. We get 2 times 5 squared minus 40, right, using this quadratic. This gives us 50 minus 40, which is 10. That means at the value of 5, my function value is going to be 10. So indeed, this is no longer an empty circle. This is a filled-in circle, because at t equals 5, the population is 10. Now let's figure out what happens at p equals 8. Using my second piece function, I have the quadratic 2t squared minus 40. This guy is going to give me 2 times 64, which is 128, minus 40, that's going to give me 88. So I know that near the value t equals 8, my population is going to be 88,000. Now notice that at t equals 8, that guy is included in this third piece here, so it's going to be an empty circle at 88. So let me just clear up some space here. We see that at t equals 8, we are going to get the function value that's really close to 88 or 88,000. So it's about an empty circle right there. And this is a quadratic, so let's connect this with a smooth curve. And this curve will technically extend, go down to the -40s, and then come back up on the negative side. But we don't care about negatives because this is population in time. We can't have negatives of population or negative time. Okay, now we have our last piece, which is this third one here, when t is greater or equal to 8. Let's see what happens at 8. So if I sub in p at 8, that gives me this third piece right here. So that is going to be 40 over 8 plus 60. And that's going to give me a value of 65. So give or take somewhere around here, t of 8 is going to be, or p at 8 is going to be that point. Now what happens as t increases? As t gets bigger and bigger and bigger, I'm doing 40 divided by some bigger and bigger number, that's going to go to 0. So eventually this thing is going to go taper off, and eventually it's going to go to 0 plus 60, which is about 60. Okay, so it's going to go on like that. So this is the graph of p of t. All right, now let's continue to answer parts B and so on. So part B, we want to evaluate the function at the point 0, 3, 5, 8, and 10. So let's go ahead and do that. P at 0, which piece of the function am I going to use? Well, at 0, I'm using the first piece here, so that's just going to be 10. But technically, the population is in thousands, so I'm just going to write it as 10,000. Okay, how about P at 3? Which part of the function am I going to be in now? Well, 3 is in the interval between 0 and 5, so P at 3 is still going to be in my first interval, so this guy right here. So P at 3 is still 10,000. Okay, P at 5, what happens? Well, at 5, I actually switch over to my second piece, so I'm going to use this guy right here. So that's going to be 2 times 5 squared minus 40, and I'm going to multiply this whole thing by 1,000 to get my actual population. So crunching this up, this is going to give us 10,000 as well. And all three of these you can actually see from the graph. P at 0, P at 3, and P at 5. Okay, now let's look at P of 8. So P at 8, when T equals 8, I'm in this second piece, or this third piece here. So I need to sub in my T in my third piece, which is 40 over 8 plus 60. And again, I'm going to times it by 1,000. So this is going to give me 65,000. And you can see that from the graph as well. P at 8 is 65,000. Our last one is P at 10. Well, when it's 10, I'm looking at this third piece here. So that's going to be 40 over 10 plus 60, all times 1,000, which is going to give us 64,000. Okay, let's take a look at part C now. Part C, we are looking for the limit as t approaches 5 from the left, right, and t approaches 5 in general. So limit as t approaches 5 from the left of P of t. Let's see what that's going to be using our graph. So if I'm approaching 5 from the left, I'm following this orange line, and my y value, or P of t value, is going to be 10. So this guy is 10, or 10,000 technically. And then the limit as t approaches 5 from the right of this function. If you follow the graph, this time we will follow the green graph. And again, we get the same value of 10. So this is also 10,000. So therefore, the limit as t approaches 5 in general, not from the left, from the right, just in general, that's also going to be 10,000 because they equal. Now I'm going to pause the video and I want you to use your graph to figure out parts D and part E. So in part D, they asked us to find the limit as t approaches 6 from the left, from the right, and 6 in general. So t equals 6 is somewhere around here. So I'm going to be using the second piece of the function, and we can calculate what happens at t equals 6, just sub in 6 for t, and we'll see that we're going to get 32, or 32,000. So that's why the limit as as t approaches 6 from the left, from the right, and 6 in general are all 32,000s. Now, for part E, we're looking at the limit as t approaches 8 from the left, right, and in general. From the left, we can follow this green piece, and that brings us to 88,000. From the right, we're following this pink piece, and that brings us to 65,000. So since those two don't equal, the limit as t approaches 8 in general does not exist. Okay, part F, this last part. At time t equals 8, that weird point right there, there's a predator actually, and this predator reduced the population significantly. So poor wildcats, there's a predator in here that killed a bunch of them. So we want to determine the number of cats that were killed by the predator at that time. So if you look at what's happening here, right before t equals 8, so right before 8 years, we had 88,000 wildcats. Just after 8 years, right after that, we had 65,000 wildcats. So this difference here is a difference of, what, 23,000? So this difference of 23,000 can only be explained by the predator. Okay, so therefore, the number of wildcats that were killed by the predator is 23,000.